Um, Hello, thanks for coming back. So we are going to continue with the third lecture, now with GovindMenon. Thank you.
So thanks very much for showing up today too. So I would like to kind of again just begin by setting the stage by just defining the problems that I spoke about yesterday, putting a little bit, including a little bit of what Dominic had said. And then what I will do after that is to actually kind of begin to give you a probabilistic feel for how to think about these results. So in some sense, what we're looking for, like, if we just step back a little bit yesterday, what I told you about is what an embedding problem is, or what an isometric embedding problem is of different sorts. And I kind of hinted at, let's say, a stochastic control scheme, which could be perhaps constructed to solve these problems. On the other hand, what Dominic presented to you was kind of like, I would say, a very profound classical theory, beginning, for example, in the late 1800s, but kind of, let's say, formalized by Weil in the 1960s to kind of explain the context of those problems, and leading up from the classical theorems into the work of Nash, which is in many cases the key goal, the place that we're really looking for the interaction between analysis, probability, geometry, and for me, applied mathematics. So let me state the problems again, and then actually let me start with, let's see, this board. Just trying to organize it best. Let me start with this board. So let me just begin with material stated in the last lecture. Isometric embedding problems. And so let me use a little bit Dominic's terminology of problem 1, 2, and 3. So problem 1 was, let's say, metric space or finite metric space embedding. And what we're given is a finite set. And you're given pairwise distances. So you have a function where I take 2 points, x and y, and I associate them a distance d of xy. And we assume that the distance of xy is positive if x and y are distinct points. And what you want so you're looking for a mapping from the set into our standard reference space, which is going to be Q-dimensional Euclidean space, such that for each pair of points, the distance in Euclidean space is going to be the given distance. Okay. So one of the things that one should ask at this point is, how do you actually formulate such a problem? So let's just take stock of that. So let's call this a distance matrix. Okay, so I've got a matrix. So let's say we are indexing x this way, y that way. And we've got a matrix which is, of course, 0 on the diagonal, and then associated to any point x and y off the diagonal, we've got the distance d of xy, if that's y and that's x. So the entries on the off diagonals are positive, but we have to remember that this is a distance matrix. So these numbers must satisfy the triangle inequality. Let's say d of xy, that's not equal to d of xz, xz plus distance of zy for all triples. So actually, a rather basic question is, how does one prescribe a matrix of this nature? Like, how do you define a metric space? Okay. So I just want to kind of wait on that. So kind of what I want to do in today's lecture is actually to kind of give you a sense in which probability theory is natural, not so much in the formulation of trying to solve this problem. So that's kind of where I was in the last class, asking kind of, can we find a diffusion that will solve that problem? But actually today what I want to convince you is that probability theory is in some sense involved at the level of the foundation of the problem. Okay, so I'm going to get to that in a couple of minutes, but first let me kind of, again, begin by reminding you of the closely related embedding problems. So problem 2 was, in a sense, it has the same element of finiteness. So what you're given, so this was problem 1, I read finite metric space, so this is graph embedding. So in this case, what we are given is a graph consisting of a finite set of vertices and information on certain vertices which are linked by edges. And the distinction between, let's say, the finite metric space and the graph embedding problem is that you're given distances only for edges. Okay, and so you're given a function d, I think I called it, okay, let me use the notation from the last class, which was rho. And so rho is a mapping from the edge set to the positive real line. And so for each edge, what I said is the way we prescribe the distances is for each edge we think about E plus and E minus denote vertices adjacent to the edge. And then what we're looking for is a mapping. So I'm always using U for our embedding. So now we're looking for a mapping which takes each vertex, the kind of abstractly defined graph, into our reference space. And what we require is U of E plus minus U E minus is equal to the rho of E for each edge in the graph. Okay, so let me call this, so in each case, let me call this star 1, star 2, or actually let's call this, fine, let me use star 2. I'm probably going to overuse my stars. I'm not as well organized as Dominic, but in each case, we've got this equation which is giving us the length information. And finally, let me look at the embedding problem for Riemannian manifolds. And so let me kind of state it again in the abstract terms, and then let me kind of give you a very concrete case. In this talk, when I'm kind of going to speak about manifolds, in order to keep matters concrete, I'm just going to focus typically on the torus so that we can draw pictures, so that we can understand where the objects live. Okay, so here we are given a Riemannian manifold, and we want a mapping which takes this manifold into our reference space. And now, as Dominic explained with kind of great precision, we define kind of the notion of a smooth embedding, which is mapping from the manifold into the space, which has full rank, whose derivative has full rank at each point. And now what we require is that, so let me write, so over here we have we are given the metric G. Over there, we're going to have the standard metric, and I'm already going to overload my terminology a little bit. So, given mg, so let E, I'm sorry, so on the left side of the board, E means an edge. On the right side of the board, E denotes the standard metric, standard Euclidean metric. On RQ. And what we are looking for is now a solution to a nonlinear system of partial differential equations in local coordinates. But in abstract form, what we're writing out is something of this form. So this is the pullback metric. And this is the given metric. And this, in abstract form, is a system of, or in coordinates, it's a nonlinear PD. So the classical geometric roots of the problems that we're talking about are really in this problem, which is in some sense kind of deep and difficult problem. These problems on the left-hand side have a more elementary character, but there are kind of certain places where actually, the kind of, there are tools over here which are kind of quite different from the tools over here. Now, just to kind of give you a concrete example of this, so that's our basic example of P3, something to kind of hang your hat on, something to think about, to visualize, to give you a sense of the intuition. So choose the manifold to be, let's say, the n-dimensional torus, Rn quotient with the n. Choose G to be the identity metric. And so now we've really just got something that can be written out as a nonlinear PD and something that can be visualized in the following way. So this is for T2. So here's, let's say, T2. And I'm trying to find a mapping from T2 into R3 such that, and so when we look at this particular problem, the Jacobian matrix of the derivatives is going to be a matrix of derivatives which has size q times n. And what we're looking for is let me actually make that a little bit more visually kind of representative. So let's say something like that, a tall, skinny matrix. And this system of equations is equivalent to the system, so something of this sort. Okay, so, think about it as something of this nature. We've got an n by n square matrix. That's symmetric and positive, so you've really got n times n plus 1 over 2 equations, q unknowns. And as Dominic explained in his talk, the kind of solvability of this PD has a very, very surprising character. It involves a delicate interplay between the dimension that you're mapping into, so this parameter q, the nature of the manifold, a topological property, whether it's, you've actually got a smooth embedding of this manifold to begin with, or whether you've got topological obstructions, and then kind of surprising phenomena, which is that you may not have smooth solutions, but you have an abundance of rough solutions. So when stated in this form, there's really no probability theory in this problem. But at a very basic level, one of the questions one has to ask is, how does one prescribe distances? And how do we think about the concept of the metric? So when we're doing analysis of this problem, the type of theorems that we think about is that I tell you, take a metric which is C0, or take a metric which is C1. So what I'm doing is I'm imagining that I've got a mapping at every point on my manifold. So, at every point, for example, on the torus, I've said that I've got a positive definite matrix. So when we formulate this problem within PDE theory, what we're really doing is we're saying that G is some point in a Banach space. It's a function from my manifold into the space of positive definite matrices. So, you think about the metric as a function. In problem 1 on the graph embedding problem, or the metric space embedding problem, you think about what's being given to you as this matrix. But here's a good problem. How exactly do you make a distance matrix? So the best way I know of making a distance matrix is using probability theory. So let me kind of show you that, and then at the end of the talk, I'll kind of build up into kind of thinking about the metric itself as kind of coming from probabilistic grounds. So that's basically my goal today, and I kind of want to end this lecture today by showing you a kind of complementary theorem to the one that Dominic stated, kind of Nash's theorem, by kind of showing you a new embedding theorem, or not so new, it's from 1994. It's an embedding theorem of Berard, Bessot, and Guyot. And it's actually a fundamental theorem in machine learning. Okay, so one of the interesting reasons for me to actually look at these problems, I kind of began with examples, scientific examples. I said, like, look at computational biology, you'll have a graph embedding problem. When you think about PDE methods, there's kind of PDEs from fluid mechanics, and there, these same sort of theorems apply, and they're kind of probabilistic reasons for looking at it. But I think one of the things I like about the metric space embedding problem is that it shows you in the simplest possible way that even something as simple as prescribing a metric, something as simple as prescribing a distance, in some ways can be thought about naturally on probabilistic grounds. Okay. So let's see. That's board 1. Let me leave this up here. Let me switch to this board. Okay, these blackboards are so beautiful. I'm a little bit worried with my clumsiness that I may do damage, but okay. Sorry? So, okay. So in some sense, the theme today is using probability theory to define So let me first do this for problem 1. And let me just state it in the following way, informally. So this is the kind of principle that I'm going to be thinking about. And rather than think about a metric as a given object, I want to think about a law as a given object. Okay? It's something very straightforward, and it's really just observation. So assume we have a mean zero. So assume we have a family of random variables. So really a stochastic process. So psi is going to be my random variable, and it's going to be a vector-valued random variable. It doesn't need to be vector-valued, but since I'm working with things which are going into a vector space, it's a little bit easier to begin with a vector-valued random variable. So then the statement is that psi, or the law of psi, naturally defines a distance matrix. So this is actually a fundamental observation in Gaussian process theory, but at this point I don't need anything like Gaussians. And the statement is very straightforward. So indeed, define d of xy to be the expected value of psi of x minus psi of y squared divided by 1/2. Okay? So I've got a random field defined on my metric space, and I'm just going to use the covariance of this random field to define a distance. So distances of a finite set of points is such a kind of primitive and simple object. All we have to do is we have to have a pairwise positive number. Okay, so clearly I want a non-degeneracy condition that psi of x and psi of y on average have to be different, but let's assume something like that, which is. But the real thing, of course, that we need to check is, so clearly this is something which is by construction positive. So what you really need to do is to just check the triangle inequality. That's really all you have to do. And that's literally a kind of two-line calculation with Cauchy-Schwarz. So so take 3 points. Okay. And then you just do the usual computation. Psi of x minus psi of y squared, let's say, is equal to psi of x minus psi of y plus minus psi of z squared. And now, do, I don't know, I could, okay, let me, so it's going to be. Or is psi of z minus squared, or, okay, it's going to be less plus, I guess the inner product between psi of x minus psi of, I'm just going to use the dot product over here. Psi of y minus psi of z. Now take expectations over here. Take, okay, so take expectations over there. Take expectations over here. And when you get to this term, just use Cauchy-Schwarz, and then just manipulate the equation, and you will find that you have the triangle inequality. So the reason I like this calculation is because somehow it actually is at the foundation of how you think about regularity of Gaussian processes, and a critical piece when we are studying kind of the regularity of Gaussian processes. So when we do Gaussian processes, the beauty of Gaussian processes is that you put your information, mean zero Gaussian processes. The beauty of Gaussian processes is that all you have to do is to prescribe the covariances. And a fundamental observation, really kind of developed in the 1960s, is that you look at the covariance structure and that you recognize that the covariance structure, which is the only thing that we're kind of looking at over here, is going to define a metric through the simple kind of formula. And so in Gaussian process theory, what you do is you say that if I'm given a Gaussian process, the Gaussian process has associated to it an intrinsic metric. So this is a kind of metric which is defined by the law of the process. So somehow just the ability to prescribe a metric, to prescribe a set of numbers which satisfies the simple criteria on this kind of particular criteria, just a distance matrix which satisfies the triangle inequality, I actually think this is the best way of generating a distance matrix. So probability theory over here is very much, for me, at the foundation of how I'm thinking about the concept of the distance. Our fundamental object is the covariance. From the covariance, we construct a distance. Have a question, Arturo? Yeah. So what I mean by family of random variables is really I'm prescribing the law of the size. All I mean by family is I've got a random variable associated to each point. So this is my index set. So I've really just got a stochastic process indexed by the set K. That's all, yeah. So it's really just a random field defined on my set. Yeah.
I have a question, Govind.
Yeah.
So is there some dynamics that people can visualize behind the stochastic variable?
I do have a dynamics, but let's hold off on that for now. I mean,
Okay.
I really want to stress just this kind of elementary property, which is that it's really related to how do you think about distances. And I'm saying that it's possible to think about distances as a probabilist. That's really, in some sense, all I'm saying at this point.
Fair enough.
So because it, like when you look at it this way, it's a very cleanly defined problem, but who gives you a distance? So one of the reasons for thinking about it this way is really that idea. Like, where do distances and where do the graph embedding problems or metric space embedding problems come from in practice? In practice, what you want to think about is you are given a random point cloud. So if you've got some point cloud, you want to think about how I associate distances to it, right? So somehow the law of the point cloud is what's determining the distances of here. So, okay? So the reason for stating things in this manner is that what I really want to do is, of course, to go back to this problem, the kind of fundamental problem for us, the kind of PDE type problems, and to kind of think about how I think about the distance. So in so what we are looking for over here is an analysis to probability map, or a kind of translation of, let's say, the geometric hypotheses into kind of what would begin to feel to us probabilistically natural. And what I'm really after, the kind of heat kernel embedding, or the kind of embedding theorem that I want to state a little bit later, really relates to thinking about this distance in relation with the Gaussian process defined on a manifold. I have to make sure I don't lose sight of my plan. So actually, there's something very straightforward over here when seen in this way, but I actually don't know if this is true, and maybe it's elementary, maybe it's not, I don't know. So here's a kind of basic realizability question. Oh, this chalk is a bit rough. Yeah. The nice chalk is there. Okay, thank you. So I don't know if this question is easy or hard. It's just maybe there's an answer that somebody can tell me by the end of the lecture. I don't quite know. So is it true for distance matrix that satisfies the triangle inequality, is it true that for every distance matrix that satisfies the triangle inequality, there exists a Gaussian family or Gaussian stochastic process such that dxy is x squared to the 1/2. So given a distance matrix, can a distance matrix always be obtained from a covariance? I think this must be true, and I must apologize if this is homework that I should have done and have not done. But somehow I just want a kind of independent, simple calculation of this. And in some sense, what I'm looking for is really a kind of complete statement that you can make this fully you can make it fully a probability theory problem rather than an elementary analysis problem. So I'm not sure if this is a super simple question, but it's clearly true that if I give you a Gaussian random variable, you can make distances. What I'm asking for is kind of the opposite. Okay. So, good problem for a graduate student. Let me also kind of just, in the last class, I kind of showed you this complicated covariance matrix and a kind of structure within it. Let me just kind of look at the graph embedding problem and the metric space embedding problem in a similar manner. So, right, so just to I'm going to be using Gaussians a lot today. And so I'm just going to introduce notation for my Gaussians. I'm first going to do it for a scalar Gaussian field so that you can see the matrix and the nature of the matrix easily. And then I'll kind of introduce slightly more complicated notation for the vectorial case. So, So let psi be our mapping from our finite set and now just into the real line. And Gaussian mean 0. And let k of xy be our notation for the covariance. And let's just rewrite. So all I really want to do is to just show you how you go from kind of that expression, which involves the expectations, to kind of relationship between distances and this matrix. So this is a kind of structure within this problem, and I kind of want to show it to you in the simplest version, in the simplest form first, and then rewrite it. So then d of xy squared is the expected value of psi of x minus psi of y squared. And so that's the expected value of psi of x squared plus psi of y squared minus twice psi of x psi of y. And so in terms of our matrix over here, what we have is it's k of xx plus k of yy minus 2k xy. So somehow we have these two matrices in the problem. We've got the distance matrix, we've got a covariance matrix, and let's just think about that. So if I write out my matrix, so if this is k, I'm taking, 2 points, let's say x and y, x and y. And so what I'm really doing is I'm extracting from this big matrix. So the size of this matrix is the size, I'm sorry, this is terrible notation. So K was my metric space, and I'm using K for covariances. I'm sorry, guys, but I need to change this one, not that one.
It will be corrected on the notes, okay?
Okay, fine.
Don't worry.
Fine. Okay, great. Let me not overdo the precision. So what's really happening over here is that you've got this covariance matrix, and when you're looking for the distance between 2 points, what you're really doing is you're extracting a 2 by 2 matrix from your this is the size of metric space. So you're extracting a kind of 2 by 2 matrix from it, And then you're taking this 2 by 2 matrix and you're kind of adding these two terms and subtracting those two terms. So this is the structure that I kind of alluded to in the last class, so I just felt like I kind of want to redo this. A slight generalization is to look at a Gaussian process, which is so I'm kind of going to switch for, that's going to be my metric space. I'm going to call it an M. And now I'm going to go into RQ. And so now associated to 2 points, so I've got like, so psi of x is now a vector with coordinates, let's say psi 1 of x down through psi q of x. And psi of y is also a vector and so I've got like q random, I've got q random variables. I need to prescribe, the covariance between each of these guys. So now what we have is our covariance matrix becomes so you see the kind of bookkeeping for the covariances is becoming a little bit more complicated, but the essential idea and the essential structure is of course very clearly related. So we here x and y belong to the metric space and 1 less or equal IG less or equal q. So if you look at the covariance tensor in this case, the kind of way you want to index it is now with a big matrix. So let's say that the size of this matrix is going to be the number of points in my metric space times the dimension. And you can organize this into blocks, where the blocks correspond to points. So, there's an x, there's a y, and so for both x and y, you've got covariances associated to each of these pieces. And now there's a little bit of bookkeeping that basically says that you have a generalization of that formula from this covariance tensor. Okay, so now there's a little bit of a calculation, but what you find is now d of xy, or d squared of xy, is basically going to be the sum from I is equal to 1 through q, kii xx plus kii yy minus 2 kii xy. So I'm sorry for it's a little bit messy, but it's basically the structure where you kind of take these 2 points, sum up those 2 terms, and subtract off those 2 terms. The cardinality of M is what I've denoted by this. Sorry, I'm sorry, I didn't hear. Yeah, I'm sorry about the inconsistency. We'll fix this in the notes. I'm somehow, I think, like Dominic and I kind of riffing off one another, and I kind of want to kind of, so I'm adapting as I go along, and I think the unfortunate consequence of that is I'm being a little inconsistent.
Just to understand the notation.
Yeah, thanks. Okay, so the point over here is that you can use random variables, you can use Gaussian random variables to describe distances. Okay, so that's really the point in this part. And so now, the difference between, let's say, the graph embedding problem and the metric space embedding problem is that if we look at the kind of constraint set, the number of equations that we have, when we look at the graph embedding problem, what we have to do is we have to look at every single pair of points, x and y. When we look at, when we look at the metric space embedding problem, you have to look at every pair of points x and y, because each of these pair of points has a distance associated to it. When you're doing the graph embedding problem, you've got a collection of points, but you've also got topological information on which points are connected to one another with edges. So the number of such constraints that you have to do, the number of blocks that we take, we don't take x and y, we only take e plus and e minus, the 2 vertices associated to each edge, and we get a version of exactly this calculation. So yesterday what I said was that, this type of covariance structure appears when we are trying to construct a diffusion that will drive us from a sub-solution to the solution of a problem. But in some sense, the kind of core calculation is actually much simpler, and it's really the statement of how do you define distances using random variables. Okay? So the reason I want to do this in this kind of elementary form is to lead into one of, I think, the place where I would like you to begin to believe that probability theory is truly deeply natural in the embedding problem for Riemannian manifolds, is that I want a notion of this concept for this particular problem. So now I want to look at a continuum of points, and I want to make the statement that a metric that's given to you, so if you're thinking in terms of analysis, what you're given is a function on your manifold or a mapping from your manifold into the space of positive definite tensors, or in this very concrete case of, let's say, the manifold embedding problem. So like I'm just looking at the embedding of a torus. What's given to me, in the kind of formal problem statement is a metric, so a positive definite matrix at every single point on my torus. And now I'm asking the following question: how do you actually define a positive definite matrix at every point on a torus using probabilistic ideas? Okay. Yeah.
Maybe this is a naive question, but I want to put this on the context of other models. So we're talking
the context of
other probability models.
Yeah.
So we have a kernel and Gaussian variables. So how does this relate to, for example, a Gaussian free field, or for a smooth Gaussian field? Like, what would be the difference?
Perhaps I can hold off on that question after I describe this, because of course with the Gaussian free field, what you're doing is you're prescribing a covariance tensor in relation to the Laplacian on a particular space. And that's exactly the concept associated with metric. Metric is associated with Laplacian. You can think about that analytically, but of course it's the generator of the diffusion, and that's where the connection. It's like the Gaussian free field is such a special object that I kind of hesitate to say anything, that there's anything deeper than that. But in a sense, like that's where I'm going to go, which is really I want to make a field in a natural way, which is associated with metric. That's exactly how we want to think about embedding problems. So I would say that, okay, I could do a separate lecture on this, but let me not get too distracted. But here's one way of thinking about it, right? The Gaussian free field kind of emerges from, let's say, the Loevner theory, right? So we are trying to understand. So where does Loevner theory come from? Loevner theory really comes from the Riemann mapping theorem. And so when you're doing something like the Riemann mapping theorem, you've got some domain, you're trying to kind of map it to a kind of particular natural domain. And if you look at the first complete proof of the Riemann mapping theorem by Kobe in like 1908, a kind of important part of Kobe's proof of the Riemann mapping theorem is you make a sequence of conformal maps. You kind of, you want to make a conformal mapping of some domain which is contained within the disk to the full disk. So you're looking for a mapping from, let me call this omega 0 to the disk, which is a univalent mapping. And so how do you make that mapping? Well, what you do is you make, through a very precise recipe, a sequence of maps, omega 1, omega 2, which kind of keep expanding. Okay? And actually, this expansion process is somehow, for me, very, very reminiscent of Nash's proof. So actually, I was very inspired by Loevner theory to kind of look for the models that we're looking at. But I don't think there's a specific relation to the Gaussian free field, but there's definitely a relation to Loevner theory, because in Loevner theory, this idea of kind of expansion is fundamental. And in kind of the isometric embedding problem, this idea of expansion, a kind of family of domains or a family of domains that's getting bigger and bigger, is kind of a fundamental heuristic. So there are heuristics, there are common ideas in terms of which you're kind of trying to do random geometry. But over here with the manifold embedding theorem, it's important to remember that what's important about these results is their absolute generality and the kind of minimality of the statement. It's really just you have any Riemannian manifold with any given metric on it, you can find an embedding. So it's not a two-dimensional theory in any way. And somehow that kind of gives it a very different character. So it's much more raw. We know much less about this problem from the probabilistic standpoint. And actually our work is really, Dominic and my work is really the first probabilistic attempt at these problems to begin with. But we're definitely inspired by kind of all the work that's being done in kind of like, areas like SLE and stuff like that. But it's much, much more kind of basic at this point in time. It's really very much in kind of a framework of like almost the classical theory, I would say, or kind of like looking back to the foundations of linear theory and saying like, okay, how could we use those ideas as inspiration? So that's a kind of longish answer to your question, but that's kind of where, yeah, so we are definitely inspired by that stuff.
Yeah. Well, it's great. Thank you.
Okay. So let me actually now switch to thinking about the manifold embedding theorem. And again, let me also draw a couple of pictures. I feel like otherwise the intuition may be missing. Okay, so with that as a little bit of warm up. Okay, let's see. I think this is a problem of abundance of blackboards. Let's go with this one. Okay, so with this as inspiration, here's let's look at the third problem. And again, let's make our basic observation. So let me first just do it from the manifold to the real line. In zero. Let's see, random field. So, assuming that that's my manifold, it would be a shame not to use the colored chalk. So, colored chalk is great for realizations. So, I want to make a function. So I want to make a function on my manifold such that I can extract the metric from this function or from the law of this function. So I'm going to work, one of the reasons for working in the torus, whenever you're doing anything with manifolds, at some level you have to get down to coordinates. And so, I'm just working on the torus so that, I've got a kind of, a very easily described kind of system of coordinates. And so the way I can get a metric from a random field is through the following recipe. And so what I want to do very much in the spirit of this is to kind of write this out as a transformation from a space of covariances to a space of metrics. So let's kind of think about what's happening over here. So not quite sure what I did. I heard some strange noises, like, like there's some body buried in the background. So what is that operation actually doing, and why is it giving rise to a metric? So, let's take our random field. Let's kind of, a bit like that, take 2 points x and y. Let's begin by writing out our covariance as the expected value of psi at x and psi at y for 2 distinct points. And one of the things that we, let me assume that that's a Gaussian random field to begin with. And so one of the things, of course, that if I've got a Gaussian field, if I do something linear to it, I still have a Gaussian field. And so let's fix our indices I and j, and let's consider so let's do a d by dxi and a d dyj of this covariance tensor. So I'm differentiating the first coordinate with respect to x, the ith coordinate of x, and I'm differentiating the second coordinate with respect to yj. And so now what I'm really doing is I'm looking at the correlation of gradients. So very much, in the spirit of, let's say, Sarai's question. So dyj at y. And so the analog of this discrete calculation, where I take those 2 points and then I take the differences between these two guys, has now become the following operation. So take your random field, take its derivatives, so look at kind of the correlations of the derivatives, and now set x is equal to y. Okay, so there's an operation. And so, over here, it's expectations, and it's kind of intuitive. We are thinking about the random fields. But as a deterministic mapping, what's really happening is that there's a space of covariance matrices, or covariance tensors for this random field. And we're getting the metric by doing an operation on this covariance tensor. And what that operation is like do a derivative in the first variable, do a derivative in the second variable, and then take x is equal to y, so go on to the diagonal. So it's a kind of infinitesimal version of the calculation that you're doing over here. Okay? So the statement over here now is, as probabilists, we have found a way to think about metrics in intrinsically probabilistic terms. So it's not so much this concept coming from Riemannian geometry for us. It's really a statement about a property of the covariances of a centered Gaussian field on our manifold. So somehow, the summary is that in each of these problems, there's a recipe for starting with a random field, taking its covariance, and extracting metric or distance information from it. It's that, that's the kind of simple statement of, simple summary of everything that I've done. And I hope I've convinced you that these calculations are really elementary operations, but unfamiliar operations, elementary but unfamiliar ways of thinking about the metric. So I kind of, the way this came about, the way this kind of question came about, how can I think about a metric in terms of covariances, really came from kind of looking at Nash's proof. And later today, I think, Dominic will present a kind of fundamental lemma of Nash, which has a kind of mysterious character. A metric is a kind of quadratic object. Covariance tensors are quadratic objects. They've got positivity properties associated to them. And somehow what we're looking for is a way of writing out a metric in terms of random fields, or writing out a metric in a kind of elementary way. And this lies at the core of Nash's proof. And somehow what I'm trying to do over here is to say that actually all of that stuff has a kind of natural probabilistic analog. So there are techniques in Nash's work which have a very natural probabilistic analog, and that really comes down to kind of just the level of the problem statement. How do you think about the metric? So for an analyst, a metric is an element in a Banach space, taking a Banach space, taking values in symmetric matrices. And over here, for us, a metric is this probabilistic object. Okay, so I should get to the point where I can state a theorem, but let me maybe going slightly slower than I anticipated, but so the summary. In P1 through P3, we may define distances such metric with from probabilistic foundations okay, so I'm going to denote this kind of abstractly. So what we've got in some sense is a space of covariances. And from the space of covariances, we, let's say, go to metrics or distances. In each case, by just doing these elementary operations on the K. And so I'm going to write it out as, I want a name for this mapping. So I want a name for this mapping. It shows up all over the place. And I was kind of looking in LaTeX, like what's a symbol that's not been used? And so I'm going to call it my diamond operator. So the abstract is that K goes to G, and I'm going to kind of write this out as G is equal to diamond of K. And so let me just focus on the problem, on the kind of metric space, on the Riemannian manifold case, where, for example, for P3, we set diamond K of X is by definition dxi dyj K of xy evaluated at x is equal to y. Okay, so in analogy with the first kind of question that I asked, is given a G, can we always find so from random fields, we can define metrics. But if somebody tells you, like, I've got a CK metric, can you actually find, in a principled way, a random field whose covariances will generate this metric? Okay? So a version of this, so this kind of way of thinking about the problem is really inspired by the proof of Nash and a particular lemma that we call the Nash lemma. And in the next class, I'm going to kind of go back to this and call this the stochastic Nash lemma. So now let me state a couple of theorems. Yes?
So the partial derivatives, they
Yeah.
are relevant, right?
The partial derivatives, yes, of course. When you're doing the manifold embedding problem, your lengths are given by the partial derivatives. So if you want to think about it in the analog of the partial derivative in the finite dimensional case is to take these blocks. You've got your covariance tensor. You take these, 2 by 2. I mean, this 2 by 2 block out. So you're kind of looking at two distinct points and looking for the distance associated with these two distinct points. Of course, when you're doing the manifold, the distances are prescribed infinitesimally, and so you have to be using the partial derivatives, right? Or another way, the one way to think about this is that your field, what you're really looking at to get the metric is you're looking at correlations of gradients. So this goes very much towards Sarai's question. The kind of critical piece for us is this kind of correlation between derivatives at different points in space, and then you kind of look at that when you bring those 2 points in space next to one another. Okay? So one of the fundamental ways in which probability theory enters into the study of Riemannian manifolds. Yep.
I have a question, very
Yep.
quick question. On that question that you posed, given G, can we always find such a K? That also implicitly.
Yeah.
So the K and its corresponding.
Right, so I'm stating everything in terms of covariances, and there's a sense in which there are moments when I'm going to be thinking about Gaussian fields, in which, of course, the covariances determine the field. But actually, for reasons that will become clear in just a second, Gaussians are not quite enough, though Gaussians give you really, really good information. Okay? Okay, so how do Gaussians naturally appear in the study of Riemannian manifolds? So, so kind of one of really the fundamental ideas in kind of Dominic and my work in, in kind of our kind of first, let's say, major paper last year, is what we really want to do is we want to think about the metric from a kind of fundamentally probabilistic standpoint. And over here, we're giving it to you in terms of covariance stances. But of course, whenever you've got a Riemannian manifold, you have always a fundamental operator which is associated to your Riemannian manifold, which is the Laplacian on that Riemannian manifold. And the Laplacian is the generator of Brownian motion on that manifold. So kind of in some sense, we want to think about G as being characterized by the Laplace-Beltrami operator, which goes with G. And so today I'll show you an analytic lemma, which kind of gives you a feeling of this. But of course, what I really want to do is to convert this now to kind of beginning to think about Brownian motion on mg. So I kind of want to lead you towards, in some sense, what is our fundamental insight, which is really that there's a purely probabilistic characterization of the isometric embedding problem in terms of distinct constructions of Brownian motion on a Riemannian manifold. And then the kind of results, the kind of form of the results that Dominic stated yesterday, lead you actually back to the classical theory of stochastic differential geometry, but with new eyes. Because one of the things that we know from the embedding theorems is there's the kind of delicate interplay between regularity, codimension, and things of that nature. So it kind of leads to, I would say, an enrichment and enhancement of the classical theory. And so that's kind of where I want to go with that. But today I just want to kind of give you a feeling for this at the kind of most elementary level, which is how do you even think about the concept of the metric in terms of a random field? And I kind of want to give you a very explicit recipe in this kind of beautiful formula of Berat, Dessau, and Gaillard. Okay, so first of all, let me tell you what the Laplace-Beltrami operator is explicitly. So, let's write G. Just the definition. So, G, what this really is in coordinates, it's, okay, so dxi times. Should I have this? I'm never quite sure. I should have this, right? It's okay? I'm never quite sure. It makes me feel grown up to put this in here. Not a real problem. Okay. Okay. So given a metric, these are the prescription of the metric in coordinates. So this gives me an n by n positive definite matrix. So Gij is the inverse of Gij. And I'm going to use capital G to be square root of the determinant of the matrix Gij. And let me just kind of state at the outset the formula. So phi is a smooth function on our manifold. And the formula for the Laplace-Beltrami operator is G. Square root. Yes, the square root appears both in here and over here. Oh, sorry about that. Yeah, of course, you're completely correct. Thank you. Yeah, thanks. Okay. So let me give you a theorem in the direction of the realizability statement, and then let me tell you why this theorem is so important in applications. So, the classical analytical theory of Laplace-Beltrami operators was a generalization of the standard theory for the heat equation. And the kind of first wave of the theory, let's say culminating in the 1950s, what people found is better and better ways of writing out eigenfunction expansions. So let me kind of, state the heat kernel and, give you a formula for the heat kernel in terms of eigenfunctions. So, just for simplicity, assume M is closed. So what that means in geometry is that it's compact with no boundary. And one of the things that this assumption makes, is it allows us to have a very nice spectral theorem for the Laplacian on this manifold, or the Laplace-Beltrami operator on this manifold. I'm going to typically just refer to this as Laplacian rather than Laplace-Beltrami. The eigenvalue problem for M. So by nice, what I mean is that you have a family of eigenfunctions, discrete family of eigenfunctions that's going out to infinity. And what these guys are solving, so I'm going to write it out in the following way. So I've got my eigenfunction. So my phi m, I'm going to assume, are normalized eigenfunctions with respect to the volume element given by this metric. So phi m is equal to 1 to infinity is a complete normal basis for L2 mg. And we may think about the heat kernel of the manifold in different ways. So So a heat kernel is the fundamental solution to the Laplacian, or minus 1/2 the Laplacian, with the standard delta function initial condition. And so the heat kernel in this case admits a very explicit eigenfunction expansion in the following way. Wait, was I supposed to stop at 4:15? 4:15? Okay. Half past or 4:30? 4:30, okay, great. Otherwise, I was like, I state the theorem and I stop. It is a great mic drop moment, but maybe I could do better than that, okay. No, I was aiming for suspense over here. So I'm going to first state this term in terms of just Gaussian processes and in terms of the realizability. So at this point, I'm thinking like an analyst. Okay, so I'm really thinking that I've got my manifold, I've prescribed my metric on this manifold, modulo certain continuity properties, such that I have a nice spectral theory and a heat kernel. I'm not yet thinking about the heat kernel probabilistically. I'm really thinking about the heat kernel at this point still analytically. And my realizability problem was that I'm given a metric, so I kind of want to go from analyst language into probabilist language. So I have to go from the metric as given to me as some sort of continuous function to some sort of natural covariance kernel on the space. So the answer turns out to being very, very clean. And so I wrote it down so I wouldn't mess it up. Okay, this is the troublesome board. I'm going to move it up. So this is a theorem by geometers. And it's a theorem that I really like because it's of its concrete nature and because of its utility. Okay. So let me define a new covariance kernel, which is obtained just by rescaling this guy. And it's going to be T n over 2 plus 1. So this is the heat kernel associated G. So this theorem has two parts, but let me just start with part one. And this is by Berard, Besso, and Gaillot. It's from 1994 in GAFA. It's actually a way step towards something else that they're doing, but somehow this paper is the first place and still somehow the only place in the literature where I really see this kind of diamond operator showing up in a kind of canonical way. And the theorem is that this kernel so recall that this diamond operator is the operator that's taking me from a covariance kernel to a metric and does almost the right thing, plus a correction. And the correction is somehow a very fundamental correction. It involves the metric, and it involves the curvature. Plus order t squared. So in the last lecture, Dominic had this kind of beautiful statement going back to Weil about realizability. And Weil, of course, was the one who really understood the interplay, or kind of, was one of the, perhaps the founder of kind of mathematical physics, the interplay. So this right-hand side over here is actually the right-hand side of the Einstein equations, okay, for Lorentzian matrix. But it's a very kind of fundamental right-hand side. It's really a statement really just about the asymptotics of heat kernels. But it's kind of a way for us to kind of think about metrics organically in probabilistic terms, and it's really take your manifold, take the associated heat kernel, rescale your heat kernel, by this particular scaling, and I'll explain the heuristics of the scaling in just a second. And then if you look at the correlations of the gradients that are, or the correlations of the gradients corresponding to the way this field is defined, then you have our realizability problem was given G, make a case such that this holds. Well, we don't have an exact answer, but we have something that is arbitrarily close. The problem is that as t goes down to 0, this guy vanishes. And so you have no random field. So you don't have an exact Gaussian field associated with a given metric. But what I'm saying is that associated to any metric, you can find a Gaussian field whose correlations are almost the right thing. And this Gaussian field is actually about as fundamental a Gaussian field as you can make, because it's really just coming from a rescaled heat kernel. Okay. So this theorem is really an analysis theorem. And it's really an analysis theorem about the asymptotics of the heat equation. So in some sense, it predates the foundation of large deviations by Varadhan and kind of Varadhan's lemma, which says that you can extract distances from metrics, but it kind of gives you a feeling that at the very kind of foundational level of how we think about metrics, we can begin to think about these foundations purely on probabilistic grounds in terms of correlation of random fields. And here's a very, very kind of clean approximation that allows you to do it. So let me just kind of give you the main heuristic. I keep putting my eraser all over the place. Actually, not just, let me state a second theorem, which is actually in some sense their main theorem. So this theorem is very important in practice because it's used for what are called heat kernel embeddings. Oh, okay, let me explain the main. 10 minutes, okay. Let me tell you what a heat kernel embedding is, and maybe then I can kind of describe the ideas that underlie this theorem and lead into our work in the next lecture. So what Nash considers is you look for a mapping from the manifold into a finite dimensional Euclidean space. It turns out that actually there are many other forms of embedding theorems. And a heat kernel embedding is an embedding from a manifold into a Hilbert space. So the Hilbert space L2. And I'm going to, yeah, sorry, Arturo. There's a question from Arturo. Yeah.
Sorry to interrupt you in here, but for
Yeah.
the right, what was wrong with t equal, I mean, making t going to 0?
Okay. Okay, so that was the heuristic that let me just explain it in 2 words. I need to clean a board for it, but. So just to orient yourself to the scalings in T, let's just look at the heat kernel on Rn. Okay, so the heat kernel on Rn would have the form e to the x minus y squared over 2t, right? This is just my standard heat kernel fundamental solution to Laplace, to the heat equation in Rn. And so t to the n over 2 plus 1 ktxy. That's a super important question. So, I really want to do it in this form. So what's really happened is that you're looking at something like this. And so the way this kind of diamond operator, you're differentiating in x and you're differentiating in y. So what's going to happen is that we're going to differentiate this expression and set x is equal to y. And we want to get something non-trivial out of this. So imagine differentiating this expression x, you're going to get a 1 over t in the denominator, and that 1 over t is going to cancel this t. So you need a t to the n over 2 to cancel the singularity of the heat kernel, and you need an additional factor of t to basically deal with the fact that you're differentiating something which has a 1 over t. And the way those theorems come about is kind of general parametrics. So you're trying to guess the form of a heat kernel in general, and you kind of say, so general, or let's say the general case. You kind of want to say that your heat kernel on the manifold with the metric G is to leading order something like 1 over, or some universal constant, t to the n over 2, something like the metric. You want to say you've got something like this to leading order. And so now again, you do, put your t in front of there. So what you find is like kt of xy in this case is to leading order t times e to the minus. And then you differentiate this guy. And in some sense, it's no surprise that as you take the points x and y close together, the metric pops out at leading order. So these theorems are actually deeply classical. It's called Meenakshi Sundaram Pleyel asymptotics. It's kind of established in like the 1930s. But I think the true modern way to see it is actually from Bardhan's lemma. But in some sense, when you're doing this theorem, it's really, I would say, an analysis theorem, but kind of we're beginning to shift from analysis towards probability theory. And so this is where it's really coming from. The heat kernel is kind of picking up distances at short time, right? So kind of very, very fundamental observation in heat kernel theory and very fundamental observation. That's kind of the foundation of large deviation theory. So that's all that's going on in terms of the scaling. Good? Okay. So that theorem actually, so you can think about it as just the way in which you describe a metric, but actually this theorem is a foundation for many fundamental numerical schemes. And yesterday when we were talking about these theorems, the role of the codimension over here is super important in these theorems. You may or may not have embeddings depending upon what the codimension is. So what we've allowed ourselves in this case is now we are kind of moving into a standard Hilbert space. And the heat kernel embedding is kind of very natural because you take a point x and you send it to, okay, now I really needed my coefficients. So this is again kind of from, okay, it's a constant, but I need to get the constant right. So this, sorry, square root of 2, 4 pi to the n over 4 t to the n plus 2 divided by 4, and then e to the minus lambda mt over 2 phi m of x from m is equal to 1 through infinity, or m is equal to. So we've associated to each point in our manifold a sequence in L2. Okay, it's an explicit embedding, provided you know how to compute the eigenfunction, the eigenvalue eigenfunction decomposition of your manifold. And the real theorem so this is from the same paper of Berard, Besson, and Guyot, 94, is that this mapping is an almost isometric embedding of mg into L2. So T is fixed, and by almost isometric, we mean that as T, like in order to get this mapping to be an exact isometric embedding, we would need to send T is equal to 0, but when T is equal to 0, you've just collapsed to the origin. So it's not an exact isometric embedding, but it is as good as you want. So this theorem is actually super important. It's the foundation of a large class of numerical schemes called heat kernel embeddings or diffusion maps. It's been used in various different forms, so Belkin and Yogi in the early 2000s, and then like Jones, Maggioni, kind of whole bunch of people. It's a very, very successful program has been kind of used for kind of implementing this embedding. And in some sense, for me, this paper was very, very important because I was kind of looking for kind of natural places where probability theory would appear in the problem. And for me, in some sense, I think this is a good place to stop today's lecture. What I'm really telling you is that probability theory kind of provides us with something which is almost canonical. And so what we want over here is, in some sense, to bootstrap to something which is really canonical and somehow is not just in L2, but in a finite dimensional space. And there have been attempts of this nature. So, somehow people start out with something with heat kernel, then they switch to kind of natural scheme. So in some sense, there is a pathway that has been existing for some time. And what we're trying to do is to kind of get this pathway into its tightest mathematical form. So let me stop today and let me just summarize with kind of the message of today's lecture, which is really that you can think about metrics as concepts on fundamentally, just on kind of probabilistic grounds by recognizing in the Riemannian manifold case that the metric is kind of tied immediately to the Laplacian and to Brownian motion into heat kernels. And in the kind of discrete case, where one doesn't have this type of exact prescription, nevertheless, we have kind of covariance matrices. And so this is the way I'm going to be kind of thinking about these problems. Okay, so let me stop at this point. Thanks very much for the attention.
Questions? Questions? No questions? Ah, okay.
I mean, in here you allowed a little bit of a slack. With the L2, you allowed it to be very large.
That's certainly true. So, you know,
I wasn't criticizing, sorry.
Yeah. No. I mean, so is that the question, or is that just
No,
a kind of
I was going to pose the question. So
Yeah.
what if you enlarge it slightly? I mean, you allow yourself a little bit more slack and allow you to be another L. I mean, are there any other constructive BBG 94 theorems where instead of the L2, you can constructively give another sort of embedding into a really large space?
Yeah, so there are actually many theorems, you know, even predating Nash's work in the 1950s, of embedding a space, a metric space, for example, into infinite dimensional spaces. So, for example, theoretical computer science often try to do, try to do embeddings into little L1. So there is a kind of large literature on this. I think our interest is very much in the Nash theorems, but a new viewpoint on the Nash theorems. Let me kind of phrase it in the following way. What I wanted to do in today's lecture is really to kind of familiarize you, or to kind of provide you hints, let's say. So I'm phrasing this as a little bit of a detective story. We are trying to find the best probabilistic description of here. And so what I'm phrasing it is like, for me, this is this is the fundamental step where one really sees for the first time a precise, explicit, and I actually in my head, I thought I would show you the proof of this theorem today. So for example, even the fact that this is an embedding is actually, it's just a clever paper, really, really clever paper. And so the proofs are kind of, you know, we could be doing it. But for me, it was just important in kind of like conceptualizing this view that probability theory is a natural foundation of the problem. What we've actually done is something different in the sense that one of the things that I don't like about the heat kernel asymptotics is, well, that it's classical heat kernel asymptotics. So let me kind of draw a picture for that. Right, so, you know, so here's my manifold, and I've got 2 points, x and y. And, okay, so I have a heat kernel is this formula that I wrote down on the board. But that's not how I want to think about the heat kernel. What I really want to think about is bridges that connect x and y, you know, taking time t to get me from x and y, and to kind of sum over the space of space. You know, I want to be doing an integral over a path space, and saying that what I'm really doing is looking at all of these paths and thinking about the heat kernel in that way. And so short-time asymptotics of the heat kernel, Varadan's lemma, so if you think about it analytically, it's really just the statement that the limit as t goes down to 0 of, let me, minus 2t times the logarithm of kt of xy is going to be the geodesic distance between 2 points x and y. So you can think about this as an analytic statement, but what it's really telling you is that the bridges concentrate as t goes down to 0 around the geodesic connecting these points. So you want to think about geodesics as being obtained from Brownian motion. So what we really want to do is to actually think about the heat kernel embeddings as inspiration, but what we really want is to prove theorems on Brownian motion. So that's kind of like the core theorem that we're after. We don't have new proofs of the embeddings, but we do have relationships, very tight relationships between Brownian motion and the embedding problem. Okay? If you have another question, I can wait, or? Yeah.
A very short one only. You said implementable stuff, so the phi's are, you can find them, the orthonormal basis.
Yeah, so in practice, well, you know, let me give you a sense of how these theorems are. So from the kind of way in which I've written it out over here, like, you could think about like, okay, let me try to make this into a numerical scheme. So I assume that I'm given some metric, let's say on a space like the torus, then I have to solve an eigenvalue problem. There are kind of well-established numerical methods for solving the eigenvalue problem. So I find the spectral decomposition of my manifold, and then from that, I make an embedding of the manifold. That's actually not how it works in practice. So in practice, what actually happens is people just have some data cloud. Let me give an example of how you get a data cloud. So imagine you're doing measurements of a patient's heartbeat. Okay, so you're kind of just taking, getting kind of like some kind of like electronic signal. Let's say you measure the heartbeats for 1 minute, then so you have a data stream, a time series. So your time series is some point in high dimensional space, and so you get this point cloud of points in a high dimensional space. So what you really do is you take this point cloud, you approximate it in some way with a graph, look at the associated graph Laplacian, compute its eigenfunctions, and what you're really trying to do is model reduction. So you want to say that this object, which is living in high dimensions, is actually low dimensional. And so what you really do is you take this point cloud, approximate it by a graph Laplacian, compute the eigenvalues of that, and say, okay, I just need the top few modes, and that gives me my data reduction. So people use it in all sorts of different ways. I feel like I should know it better than I actually do, but I've just been using it as inspiration to kind of really, again, for me, just work from probabilistic foundations towards these kind of fundamental math theorems. Yeah.
More questions? No?
I think Sarai had a question over here.
Yes. You have a question, Sarai? Okay.
I think it's related to your answer to Arturo's question, because I was wondering if you can do anything meaningful when you are back in the context of a graph, but then you look at the hit kernel of the simple random walk.
Yeah, yeah.
So
Unfortunately, you don't have short-time asymptotics on an arbitrary graph. So this does not apply.
Yeah, you need like some conditions, right? Like
Yeah.
the
So
size of your intrinsic
You need all sorts of
volume,
things.
these doubling conditions, stuff like that.
Yeah. So let me say, however, that one of the reasons for me to kind of do the metric space, the graph embedding, and the manifold embedding together actually, again, in some sense goes back to the paper of Berard, Besso, and Gaillot, and actually to work of Gromov, where you really just want to think about a manifold or the manifold embedding problem. Somehow you want to think about point clouds, the embedding of point clouds, and the embedding of continua as somehow coming from the same roots. So you kind of want to make distance fundamental much more so than the topology. So it's definitely the case that, of course, when you're doing the heat kernel and then you look at the graph, you want to do the random walks on the graph instead. But of course, again, in all of these things, the devil is always in the details. And so I use those as inspiration. I want to use those for numerical schemes, but my heart is very much in the manifold embedding theorem.
Thank you. Okay, well, so now let's thank Govind again for the third lecture.